Thank you very much for having me here. I'm going to talk today about the, on the topic virtual to actual, about tools of collaboration. And by tools of collaboration, I mean tools that we develop in our office to help support projects, design projects which we carry out in collaborations with architects, artists, and designers of different types. One of the projects where structure and architecture interact from a design point of view in a more kind of integrated way are facades. I've selected here a few projects which are maybe some of the smaller projects that we carry out at AKT, and particularly my team part. Projects that happen very quickly and allow us sometimes to really test the materiality and the tools more hands-on over a much shorter period of time. So they're almost prototypes for the bigger projects. Now this is a collaboration we did with Asif Khan. It's the Coca-Cola Pavilion, which we designed for the Olympic Park. The original idea that you saw in the competition image was this scatter of objects, of pillows that form the facade. And what we were intrigued was to see whether we could find a structure. And by structure, I don't just mean beams and columns. I mean an organization in space that could allow us to actually realize this kind of chaotic or random scatter of objects. And you saw some simulations. We had pressures both from the contractor and from the client being Coca-Cola, saying we have a very sleek, simple branding, all that chaos is a little in competition with all of that. And the contractor had 6 months to deliver this on site, and obviously they were concerned about the repetition. So we came up with an idea of a reciprocal system. Reciprocal systems are systems which are actually quite simple. This is a trick we always used in the pub to describe the principles. It consists of a kind of loop of rigid elements transferring load to a stiff boundary. So in a way, it's a device for spanning a long span, but with very short, discrete elements. Now, what we were intrigued in this idea, in this particular project, was to see whether we can compact this and create a complete three-dimensional packing, which would allow us to use these pillows. And the idea was to use 5-meter-long ETFE pillows with interactive sensors to produce music and sound. But the problem was to generate something which was regular because of repetition and simple to build, but at the same time sufficiently flexible to be developed in a design, as a design. So we developed this framework based on a kind of reciprocal tiling. You can see here, it does have a certain sort of musical sequence to it, a kind of numerical sequence that sort of expresses it, expresses a kind of regularity. We use this tiling on this packing of reciprocal object and wrap them around the form of the building, and use this as a kind of three-dimensional scaffold, a structure, an organization that we could inscribe these pillows, these ETFE air beams, because they were also structural in the way that we packed them, and self-supporting. And we, within this sort of rigid framework, we allowed a couple of sort of moves. One was the possibility of sort of sliding the pillow along its length, and then the other one was to flip it around its axis. And what this would allow us to do is to basically create a variation and a certain responsiveness also to the side, to the views, and allow design. So going back to the idea of a kind of collaborative tool, this effectively allowed us to sit down with Asif and develop a design which was almost crafted with a simple digital tool that had the intelligence of making this a simple modular system. And the last drawing we ever issued on the project was probably only a couple of days before this was all going to be assembled on site. And it was the spreadsheet that told the contractor how far he had to slide each pillow or flip each pillow in order to set it out in this sort of rigid framework of connections. These are the pillows. They are interactive and responsive. So it's a facade that obviously requires a very close design with the artist or the architect because it's performative in this sense. In this particular sense, it's more than a building. It's a musical instrument. It's something that responds to the touch. But we also wanted this to be self-supporting and structural. So it was very important for us to connect it in a way that where sort of every pillow didn't require a single cantilever bracket. So we came up with these clips that sort of held two pillows in this reciprocal arrangement and stiff enough and redundant enough in order to create a self-supporting system. This work also led us to develop this sort of approach of a kind of integrated facade, led us to invest quite a bit of effort in some projects to develop structural skins. In structural skins, the structure is embedded within the grain of the element. If we take, for example, the BMW Pavilion, which we designed with Siri architects, this consists of a series of sort of lily pad shapes forming the canopy of the BMW Pavilion, again on the Olympic site. It's a simple boat building construction, so we could get any carpenter from close by to build it. So 3 layers of cross-laminated ply with a series of internal joists. A very simple construction that we were able to unfold as an IKEA pack and get them to build in a simple way and with simple tools. This is the sort of catalog. I mean, stress skins are very efficient structures because they mobilize the whole skin, the whole cladding of the building as a structural element. So, and they have a great degree of redundancy. So what we could achieve were very long spans. The longest span was about 18 meters. So more or less the size of this stage and about a foot deep. It could all be built in pieces, bolted together, and spliced on site. Of course, when you work very closely with craftsmen, whether these are sort of designers who are really interested in the form and on the performance of buildings or art installations, or whether these are contractors or fabricators that deal with the physics of building these things, we're very interested in simulating the behavior of materials. So in this particular installation, which we did with Akisha Hirata at the Architectural Foundation last September, we were interested in seeing what the most natural form is for a piece of stress skin ply when you try and sort of form it into a loop. So we simulated the behavior of this loop, both in 2-dimension and 3-dimension, to create the most natural curving object. So it could all be made out of flat sheets. So this is a bit show a kind of history of the process of building it, a scaffold which got skinned. You can see the holes where the contractor could then, they would take apart these modules and then rebolt them back on site. So it was all pre-assembled. And this became a kind of continuous ribbon in space at the Architectural Foundation where Akisha sort of displayed his work in a kind of almost 3-dimensional space. Again, the efficiency in this ribbon allowed us to keep it very thin. And of course, these ideas can be extended to larger structures, larger facades. We looked at traditional materials, but like timber and steel, monocoque constructions, but we're also intrigued in seeing what would happen if we used a really strong and really rigid material like carbon fiber. So in this project with Kusama, the Japanese architects Kusama and Mark Thorness, we generated a very large pavilion. Again, it's about 5 pods, 5 meter in diameter, intersecting into a single span of about 18 meter. And the whole construction is only 2 millimeter thick. It's all generated by the pleating and the folding of the surface, which, albeit perforated by Kusama's patterns, is extremely efficient. And when obviously there's a very close collaboration with the artist where we measure the deformation and the strength of the material, and then we feed that back into a new analytical process that looks at buckling in a very sophisticated way. And the whole pattern of the holes was sort of informed by rules which allowed sort of structural stability, but at the same time were kind of integrated within the aesthetic of the piece. Of course, we work on larger scale projects. This is the Algiers Presidential Palace with Zaha Hadid, where we're doing simulations of form finding simulations. We're using a dynamic relaxation algorithm and physics engine to sort of form optimal shell construction. We developed tools that allow us to both determine the optimal catenary form that some of these vaults take, but also the ribbing patterns that could be expressed architecturally. And at the other end, and you can see the spectrum is quite large because what we're trying to do is to sort of see, well, to capture all the opportunities in the market between a kind of architectural design and art and artwork, in art installation. This one is a moving bridge. So through this project, understanding the optimizations that are required within a dynamic structure. And here, this consists of 5 beams, basically each counterbalanced by a counterweight. It's a very simple piece, but what we wrote is a piece of a definition in Grasshopper which allowed us to optimize through a genetic algorithm the shape and the size of the counterweight such that the load was completely minimized and the force on the pistons that would activate the structure were minimal. So I'm going to skip quickly I'm just going to say 2 words on this. We ran one of the clusters here at Smartgeometry, which is just finished, and this was based on the idea of trying to pull the kind of the research on digital tools that are able to simulate the behavior of physical behavior of folding structures and the digital means of creating these in practice. So these are some of the early models that show these deployable structures. The idea is to create skins, structural skins, facades and building envelopes, which are able to adapt to different structural loading patterns and adapt their shape, their volume. We use very low technology, obviously, for this particular workshop. We use sprung steel as actuators that would just buckle and allow us to sort of fold the structures. These are some of the early prototypes and images. These are some of the tools in Kangaroo which we developed, which sort of generate those physical behaviors. And this is actually one of the joint which we ended up building, which uses these sort of sprung steel struts made of measuring tape to sort of make the structure rigid. But you could imagine that those actuators could be hydraulic and they could generate actually a moving structure where the volume of the building could potentially vary and the skin respond to other inputs like climate and so on. This is we had someone in the cluster who was looking at sort of daylight and how that could be optimized. This is just the beginning of an exploration. I'm just going to let this run. It's just a few images from the cluster, and we're hoping that this could lead to future sort of experiments in sort of structural adaptive skins.